Okay, so let's go ahead and take a look at section 2.2, which is an introduction to the finite difference method. And so we're going to go ahead and start using Excel to solve some of our problems. And so we're going to do a short derivation for this method in this lecture. All right, so like before, we're still going to have a control volume. And so you recall this picture we had before when we discussed making a control volume through a sheet. Well, we're going to still have a control volume. It's just now we're going to start numbering these, and we're going to eventually think of each of these volumes as being a cell in Excel. Okay, and so this would be a row through Excel, and each of these would have values corresponding to the concentration that's in this one region. And that region would represent the volume here of our control volume. So what we're going to do is a mass balance again, just like we did before, but now we're going to do it on this volume, and our volume is now going to be finite, and so we're not going to be deriving the differential equation anymore, but we're going to be just simply doing a mass balance for this little volume element. And so what we can do is break up our solid. Once we have a known thickness, we can break it up into a number of nodes or points, and the distance between these nodes, so the centers of each of these control volumes has a node in it, the distance between them is just going to be the length, or the thickness of our solid, right, divided by the number of nodes minus 1. And so we've got 1, 2, 3, 4, 5, 6, 7 nodes, so delta divided by 6 would be our spacing. And you could see that here, because if you count the actual spacings, right, this is 1 spacing, 2, 3, 4, 5 spacings, 6 spacings. Okay, so we're just breaking delta up into 6 spacings. All right, so let's go ahead and take a look at this node 4. So we're going to go ahead and perform this mass balance. Looks like some of this is off screen. All right, so we're going to go ahead and perform a mass balance on this, again, just like before. And again, now our volume is a delta x in thickness. Okay, that's the same as the distance from C3 to C4. Our volume element is halfway between nodes 3 and 4 to halfway between 4 and 5. Okay, so node 4 takes up this space. So we still have fixed first law. And we're going to go ahead and rewrite fixed first law in the linear case of delta C, delta x being linear. And we're going to go ahead then and write this in terms of, if I'm looking at this flux in, I'm going to go ahead and write this delta C, delta x in terms of these variables. So my J in flux is minus D times C4 minus C3 over delta x. Okay. The order of this is important. Remember that we're going to always point our x direction to the right, and so that's going to be considered positive to the right. And so when we do a delta, it's 4 minus 3, and then it would be 5 minus 4. Okay. That's the order in which you have to do the delta. So we have C4 minus C3, and then likewise the flux coming out would be given by C5 minus C4 over the distance between them, which again is delta x. And so there's my outflux. So now I have an influx related to 2 concentrations and an outflux related to 2 other concentrations. And so I could calculate the difference between these now. And the difference then is going to be related to whether the concentration in this volume element goes up or down. So let's do that. So the rate of accumulation of mass, just like before, is the rate at which the mass enters minus the rate at which the mass exits. Okay, this is exactly what we had before. Okay. Now we're going to go ahead directly from this equation here. So we have dc dt is J in minus J out over delta x. And so we've got minus d c4 minus c3 over delta x, and we've got minus d c5 minus c4 delta x, and then recall that we're now subtracting because it's in minus out. And then when we divide through by the volume term and we cancel the areas that come out, we would end up with a delta x on the bottom. So that's where this came from. All right, so dc dt then is just equal to, if the d is constant, and we can pull this delta x out as well. That's a constant, and so we have d over delta x squared, and then we just have minus c4 plus a c3. We've got a c5 minus a c4, and so we put them together, and we have c3 minus 2c4 plus c5. So we now have how the concentration changes at our node 4 based on constants that we know and concentrations around our particular node. Well, dc dt can be written this way. So this delta t, first of all, is just our time step, and dc is for node 4. That's what we derived this for. So it's the value of the concentration of node 4 at the next time interval minus the concentration of node 4 at the present time interval, right? That's a change in concentration with respect to time. And so this is going to tell me then how the concentration changes at node 4. So this is a delta C at node 4 in time. All right, so let's go ahead and bring this over, and we'll bring this one over as well. And so we finally get our node equation that defines how the concentrations vary at each time step. It's the previous time step plus the change. And the change here is given by d over delta x squared times delta t. Right, when I brought it over, we're going to call that the Fourier number. And then we've got our parameters c3, 2c4 plus c5. Okay, so these values are all from one time step, and the Fourier number here has our time step built into it. So if it's delta t is 1 second, then 1 second in the future, we now have the value here for c4. So we've got to see how this works in practice, but this is fairly simple. If these values are all given, which they are, you just simply plug it in. And these are all constants. So we can definitely plug in and get our next value. All right, so here's our equation again, and our sketch for what's going on. And so the way to think about this is, again, is that we have a time t. So in Excel, we're going to have each of these nodes are going to be there in Excel. They're going to be in a row with values. And that's at my time t. So that's all of this. Everything's known. These are all known numbers. And then we're going to go ahead and calculate for a time step later. That'll be in my Fourier. Remember, that's got delta t in it. We want to calculate what the new value of C4 is, node 4. All right, well, according to this equation, all we got to do is take this node 4 value, subtract 2 times the Fourier of this value, and then add to that the Fourier times this one, plus the Fourier times that one. And that will give us our new value for C4. So there it is. So if I'm given the initial values of these, I can simply calculate what they're going to be in the next time. All right, so I can run through all of these and do that, and I'll get another row of values for a later time. And I can take those and then continue this process and go to the next time step. Okay, so for general then, for a node I, right, I'm just going to take the value of node I, I'm going to take the left of the step, I'm going to take the value I, and I'm going to take the right side, right? So here's my random I, take the left, value 1, take the right. All right, so if we were to apply this technique to the decarburization case that we did last time, I went and plotted here in the solid lines the exact solution that we derived last time. And then in the dotted lines, the dotted symbols, that is the value I got from the finite difference method, plugging them into these equations and moving out to 120 seconds. So it took me several time steps because I'm going to let my delta t, my time step, be 5 seconds. And so 5 seconds later, if I was to go through and calculate all this, I'd end up with this red curve. Okay. And my blue curve, the one I'm going to need to calculate the next step, is the values are all given here. Okay. So what you can do is to go ahead and pause the video and make sure that you can do this calculation. So what I'd like to calculate is at a depth of 0.1, I want to calculate what that value is at 125 seconds. Okay. And I'm given 0.1, I'm given its value, concentration, I'm given the node to the left of it, right, and the node to the right of it. All those values are all given. Okay, so this is my 0.1 value, so I'm sitting here, and you have that one, you have this one, and you have that one, and you want to calculate the new value of it, which would be right down here on the red curve. Okay, so you have those. So from my equation here, then if I want node 0.1, then this is also a 0.1. Okay, just at my step that I already have values for. Fourier, and then this would be the node to the left, which is 0.08 in this problem. The one I'm on, 0.1. The one to the right, 0.12. Okay, so I pull those again straight from this table. So that's going to be my 0.8 one, my 0.1, my 0.12. Take those three numbers and you just plug them into this equation. So there they are. We calculate the Fourier. The delta t is 5 seconds because we're going from step 120 to 125, so that's 5 seconds. So that goes in. These other two are givens. We calculate that Fourier number. That goes out front. Plug in the concentrations. Now we have my 0.1 value at 125 seconds. All right, so you go ahead and again pause it here and calculate the concentration at a depth of 0.08 now at 125. So just repeat this kind of calculation. Test yourself. I'm going to show you the answer here now. So if you're going to do this, go ahead and pause it, and then you can come back and I'll show you. All right, so here is the answer for it with the numbers plugged in. You can double check your work. All right, so this is what we were given. Just kind of a zoom in here. This is the one we just calculated in our example. The one down here is the one you calculated just above. And another self-test is shown below, which will give you this point here. If you want to try that one out, there's the answer, and you can give it a try. Now, if we were going to get the concentration at this position for 130 seconds, then what we need to do is calculate all the ones on the red curve for the 125, then use those values back into the equation, and we can get the 130 second ones. And so that's the idea, and we just keep going down, continuing in time, and adding more and more concentrations. So relatively simple process. So we're going to go over this in class. So make sure you can go back and try and make one of those calculations or two of them by hand so that it makes sense. And then what we're going to do in class is we're going to go through and do this actually in Excel. So you have this in your Canvas site, so you can go ahead and download that file. It's just a kind of a starter. And we're going to go ahead and look at this carburization or decarburization problem again. And I've numbered already in the sheet the different nodes. Looks like in this particular case I used 51 of them, so we have a much more accurate answer than just a few nodes I was using a second ago. But we're going to use 51 nodes, which will end up being a dx then if you take our thickness divided by, which is 1 millimeter, divided by 50, right? 51 minus 1. And we're going to get, what do we got? 0.002 millimeters. Okay, that's will be our step size, or 0.02 millimeters. Here it is. So that's our step size. Okay, we'll fill this in, and notice that at the time equals 0, that's initial conditions, we have values. So we always have those. Those are initial. That means I can use this equation now, take these values, and calculate the next step after 5 seconds. I can fill this row in with this one equation, and then I can take those values and I can calculate now the 10-second step. And I just keep repeating this, and I'm going to get my time-dependent concentration curves. All right, see you in class.